couple of days ago, we identified 5 different shapes of position time graphs. If you remember, all 5 of these position time graphs have time on the x-axis because time is the blank variable. Manipulated variable, right. The manipulated variable always goes on the x-axis of the graph, and the responding always goes on the y-axis of the graph. The title is always y-axis versus x-axis, responding versus manipulated, or in this case, it's position versus time. Now, 3 of these graphs have straight lines. Straight lines, one's sloping upwards, one's sloping downwards, and one's just nice and flat and horizontal. If you see a straight line, give me a word that would be synonymous with straight line. Not necessarily even on a position time graph. Just a one-word answer. Something that's synonymous with straight line. You could say uniform, or somebody else said constant. Constant or uniform, either one of those would work. So it depends on the graph. What is constant? What is uniform? Okay, I got a position time graph, something's constant. If I have a velocity time graph, something else is constant, but something's constant. Tell me what's constant on a position time graph if I have a straight line. What is it? I thought I saw your mouth moving there, Solana. Yeah, it's constant velocity, right? This would be, all 3 of these are constant velocity. Specifically, this would be a constant positive velocity because it's sloping upward. This one would be a constant negative velocity because it's sloping downward. What about this one? This would be a constant velocity of 0. You could say that, constant velocity of 0 if you got this question on a quiz or a test, but you could also say what? What means the same thing as a constant velocity of 0? It's at rest, or it's stopped, or something to that effect, right? I'd accept any of those as answers if you get this on a quiz or a test. I'm just going to say stopped because it's less writing. Now, the 4th and 5th one, you see these 2 both are curving, which means you do not have a constant velocity. If you don't have a constant velocity, then it must be accelerating, right? This one would be what kind of acceleration would this one be? Yeah, it's a positive acceleration. That means it's speeding up. This one would be a negative acceleration, which means, in this case, that it's slowing down. So a straight line means constant or uniform. On a position time graph, that's constant or uniform velocity. If it's a curved line, it means not constant, not uniform. Well, in this case, it's not uniform or not constant velocity, which means it must be accelerating, either a positive or a negative acceleration. You guys remember how to find the position on any of these graphs? Let's say I want to find the position at 5 seconds on each of these graphs. What would I do? 3 words. Up and over. Yeah, up and over. If you want to find the position on a position time graph, the velocity on a velocity time graph, the momentum, whatever the heck that is, right? The momentum on a momentum time graph, the force on a force time graph, the whatever on a whatever time graph, you're always just going to go up and over. Now, if position is up and over, and displacement is defined as the change in position, well, then we could find the displacement by doing what? Up and over twice, and then subtract the 2, right? The displacement is the final position minus the initial position. So if df is going to be found by going up and over, di is going to be found by going up and over, and then I'm going to subtract the 2 of them. So up and over, subtract the 2 of them. Final minus initial position. And finally, your average velocity. Average velocity isn't any different than it ever is. Okay, everything we've done to this point with average velocity has been the same. To find the average velocity, what are we going to do? Displacement over time. Yeah, we'll just use the equation, displacement over time. Now, if it's a straight line, the average velocity will be the same as the slope of the graph. When you guys did your lab activity, you found the slope of the graph, right? Or Google Sheets found the slope of the graph, which corresponded to the average velocity, right? That's because it was a straight line. The average velocity is always delta d over delta t, and if it's a single straight line, that corresponds to the same value as the slope of the graph. Finally, instantaneous velocity. The only way you can deal with instantaneous velocity right now is if it's on a perfect straight line. If it's on a curved line, you can't deal with that yet. It's coming, but you can't deal with it yet. If it's instantaneous velocity when you have a graph like this, you can't deal with it unless you look at just this straight line or just this straight line. The average velocity in this green circle here, let's say it's 5. The average velocity in this red circle is, let's say, well, it's 0, right? Because it stopped. If we wanted to find the instantaneous velocity anywhere along this green straight line here, we would say the instantaneous velocity would be 5. The instantaneous velocity anywhere along this red one is what? 0. Now, you couldn't say like, oh, the average overall is whatever the overall average is. Let's say it's 2.5, 3, let's say. You couldn't say the instantaneous was 2.5 or 3. You have to look at one line or the other, one straight line or the other. Make sense? Okay, I gave you a couple questions, well, 10 questions to work on. Just involved 2 graphs. We'll give you some answers to those, and then we'll take a look at, I'll take a look at a few of those questions, all right? At the special request of Maddie and others, let's do the second graph. The second graph. If we have any trouble with the first graph, questions 1 through 6, ask me and I can help you out with that. Okay, but we want to go over at least one of these to make sure that you're okay with it, even if you get the right answers. Okay. So question 7 relates to this graph here. We say, what's the displacement of the object between 0 and 10 seconds? Well, displacement is final minus initial position, right? And position is just up and over. So all we're going to do for this is say up and over, and then subtract the 2. 10 seconds, oh, that's easy. The position at 10 seconds is 0. The position at 0 seconds is, looks like 14. Is that right? So we're going to say 0 minus 14 meters, which is negative 14 meters. By the way, west is positive since it's west on my graph. So negative 14 meters, or, wait a second here. I'm going to say negative 14 meters. Yeah, I think when I gave you the answers, I said negative 14 west. Did I say that? No, I don't know. I don't know what I said. But it should either be negative 14. Let me think here. Yeah, you could say negative 14 west, right? Because it's east. It's going, the displacement is to the east because you're going backwards. Yeah, you could say that. Negative 14 meters to the west. Yeah, that works. 8. The displacement between 10 and 18 seconds. Between 10 and 18 seconds, we're going to do the same thing. The final minus the initial position. The final position at 18 seconds, if we go up and over, looks to be 6 meters. At 10 seconds, it's 0 meters. 6 minus 0 is 6.0 meters to the west. 9, the average velocity between 10 and 18. Average velocity is the slope of the graph, right? If it's a straight line. But the easiest way to find the average velocity is just to say displacement over time. The displacement between 10 and 18 seconds is 6 meters to the west. And the time here is 8 seconds between 10 and 18. So that's going to be 0.75 meters per second. I defined west as positive, so positive means west, right? Really, I didn't need to write in west here either, I guess, because positive means west. And finally, the average velocity between 0 and 18 seconds. Here's where I could not use the slope, right? Because between 0 and 18, I got 2 different lines. But I can still use v is equal to delta d over delta t. That always works. So let's say my displacement, well, I haven't found that yet. My displacement between 0 and 18 is my final position, which is 6 meters, minus my initial position, which is 14 meters, divided by my time interval between 0 and 18, which is 18. So we're going to say it's negative 8 divided by 18, which is negative 0.44, is that right? Negative 0.44, which is to the east, right? Good. You guys okay with those? Okay. Now I want to show you something else with a position time graph. Going to get you to take out your calculators for this one. This is more of what you saw in your lab activity, right? Points on your lab activity were closer together, but these are data points. They're not on a perfect straight line, but it looks like they're pretty darn close, right? So what we're going to do with this is draw what we call a trend line or a line of best fit. You guys did that on your lab, except, well, Google Sheets did it for you. And then we're going to find the slope of it, like you did in your graph, except that Google Sheets did it for you in your graph on your lab. To draw a trend line, what you want to do is take a ruler. Ideally, it's a clear ruler, but it doesn't have to be, or any straight edge really for that matter, and draw a line that approximates those data points. This line does not approximate those data points, nor does this one. This one that I'm about to draw is better, but it's not quite right. Right? It's not approximating these data points as good as, say, this one is. Make sense? Now, you don't want to do this freehand. It's just a little bit hard for me on the smartboard to use a ruler, so that's why I'm doing it freehand. That's your line of best fit. But the good news is, if you have a TI83, TI84 calculator, there's a nice, easy way to find the slope of this graph perfectly without worrying about if your trend line is perfect. If you don't have a TI83, TI84, that's okay. If you don't have a TI83 or TI84, then what I want you to do is pick 2 points on the line, far apart from each other, and then say V is equal to delta D over delta T, which is dF minus DI, up and over, subtract the 2, over TF minus TI. That's the same thing, by the way, as saying rise over run. What's rise over run equal to? Slope, right? Slope is rise over run, or y2 minus y1 over x2 minus x1. Exactly the same thing as saying df minus di over tf minus ti. V is equal to delta d over delta t is exactly the same thing as the slope. If you have a TI83, TI84, you're welcome to do this. If you don't have a TI83, TI84, you've got to do this. Draw your line of best fit, and then pick 2 points on that line like I have, and then do df minus di over tf minus ti. If you have a TI84, or 83 for that matter, which most of you probably do because of math class, right? Then there's a nice way to spit out the data that Google Sheets spits out for us. That is the slope and the y-intercept of the graph. So I want you to bear with me on this, and I want you to follow along on this. What we have to do first is identify the xy coordinates of each of these points. The xy coordinates of each of these points. Okay? It looks like each of these lines is going up by 0.4. Right? 0.4, 0.8, 1.2, 1.6, 2. Each of them on this axis is going up by 0.4, and on this one, each of them are going up by 1. So, what are my xy coordinates, my ordered pair for this one here? It looks like 0.8 and 0.8, and what would that be, 2? Right, 0 over on the x-axis and 2 on the y-axis. Does that make sense? My next one would be, what is that? 2, this would be 1.6, 1.8, 1.8 and 4. This one would be, this is 2, 2.4, 2.8, and 6. Next one is, oh, that's a little tough here. 3.6, 3.8, looks like 3.9. and 8, 4.4, 4.8, looks like about 10, 5.6, 5.7 we'll call it, close enough, and can't tell, is that about 7.5 it looks like, or sorry, 12.5? And my last one, which is 6.4, 6.8, 7.2, and 14. So those are my ordered pairs there. You think like, well, man, I might as well just found the slope of this graph, right? Like the old-fashioned way. Once you've got this, though, once you've identified these ordered pairs, which don't involve a calculation, then we got a neat little trick on our calculator that we can use to have Google Sheet or have your calculator do all the work for you, or do the rest of the work for you. So open up your calculator. And remember these this series of 6 keystrokes. Stat, edit, 1. Okay, stat, pick edit, pick 1. Stat, edit, 1. Got it? Let's say it. Stat, edit, 1. Stat, edit, 1. Click enter. Now it's going to give you a table. Now what I want to do is enter all my points here. I'm going to say 0.8. These are my x coordinates. 1.8, 2.8, 3.9, 4.8. Again, all my x coordinates here. Uh, 5.7 and 7.2. Now let's go up and fill in all my x's, or sorry, all my y's. My y's are, I start at 2, 4, 6, 8, 10. I said 12.5. It looks like, by the pattern here, it looks like it might be supposed to be 12, but we'll go with 12.5. And 14. So what did I do? Stat, edit 1. Stat, edit 1. Stat, edit 1. Then you enter your data. Now it's time to get some numbers from it, okay? Slope and so on. Now, you went stat, edit 1. Now we're going to go stat, scroll over to calc, down to option 4, linear regression. Stat, edit 1, stat, calc 4. Stat, edit 1, stat, calc 4. Stat, edit 1, stat, calc 4. Now watch what happens when I hit enter now. Sometimes, depending on your version of the calculator, you might have to hit enter a couple of times. You might have to hit it 3 or 4 times. Not a big deal. Just depends on your version of the calculator. Enter. Keep getting enter until I get an answer. Calculate. All right. That tells me the slope of my graph. The equation for my graph, y equals ax plus b. The slope of my graph, a, is 1.95. And the y-intercept of my graph is 0.535. Stat edit 1, stat calc 4. If you use that, instead of drawing a trend line, a line of best fit by hand, and calculating the slope the old-fashioned way, you almost can't go wrong. Okay, if you draw a trend line and then find the slope of that trend line, you better hope you do your trend line correctly, right? And it's easy to draw a trend line off a little bit. Yeah, question?